So today is, man, March 16th. So this is the beginning. If you're following along in that in the free book that I posted, the ebook, is actually chapter 4, and it is stoichiometry. That's a weird word. You're going to hear it a lot. We actually there's a lab coming up for those of you who are taking the lab with the class. A limiting reactant lab that is a master class in stoichiometry, because finding limiting reactants and finding the relationships between the start materials and the products, that's all stoichiometry is the study of the relationships between the start materials and the products based on their ratios. I'm just going to condense that down. So in a given, and this is just an abbreviation for reaction, RXN, in a given reaction, we can study the ratios of the substances, and that's all stoichiometry is. That's why it's important to know how to balance, because if it's not balanced, then you're gonna have the wrong ratios. And if you got the wrong ratios, then that means that you're gonna violate that principle of conservation of matter, right? Because if the numbers are not balanced, the number of atoms isn't balanced, and what you're going to find is that you violate the principle of indivisibility. You also violate the principle of conservation, right? So you don't want to do that. All right. So this chapter has 5 sections, and in the first section, this is just a chapter outline. Find that it's helpful to kind of give our brains like a map as far as where we're going. That helps a lot in keeping us focused. All right. So obviously the first section is writing and balancing chemical equations. And when you think about right, that's just an abbreviation for equations, E, Q, and S. If you think about all the stuff that we studied up to this point, right? This is why it's important to know your polyatomics, to know their charges, to know how to take a name and convert it into a compound, and vice versa. Because if you don't know the language and how to translate a name into a compound, knowing what nitrate looks like, phosphate looks like, oxalate, if you can't do that, then it makes this section even harder, because some of the problems are written out, like it'll write the name out on purpose, and you have to take that name and turn it into, write out what the symbolic part of it. So that's why all the time we spent with naming, and we spent on polyatomics and knowing iron 3, iron 2, cobalt 3, cobalt 2, that was on purpose, right? To prepare for this section and to prepare for everything going forward. So the first part is going to be writing and balancing equations. And then we're going to look at different classes of reactions. Right? We're going to look at stoichiometry. Right? And again, that's just the relationships between the substances, and we find out the stoichiometry based on what the balanced equation is. Because when you balance an equation, you need coefficients. and those coefficients that are in front of the compounds to make sure everything is the same on both sides. Those are your stoichiometric relationships. So we're gonna tie all that in, and then we're gonna talk about percent yield and theoretical yield. Very important concept. I have students in organic who still struggle with calculating percent yield. So we're gonna beat that dead horse until we can't beat it no more, because that's a very important concept to understand. And then we're gonna do some analysis, chemical analysis. That's the last part of the chapter. And it looks like a lot, but a lot of this stuff kind of folds in together, because we can talk about classes of reactions and balancing and stoichiometry all in at the same time, depending on what type of reaction we're looking at. All right, so these are the sections, and we're going to start out. And again, what we're trying to do is we're trying to accomplish some things. And one of the things about studying chemistry is understanding the connectivity between concepts, right? So when we do balancing, we're connecting the laws that govern reactions with the reactions themselves. We talked about Dalton's atomic theory and how you can't make new atoms, or an atom can't, one element can't split and become two other elements or whatever. We talked about all of that. Now we get a chance to connect it by looking at the actual reactions, and we do it subconsciously, right? With the understanding, oh yeah, we can't do that. This has to be the same on both sides. You know, if it's a compound, then it's got to combine in small whole number ratios. Like all the stuff that we talked about in the preliminaries, now it's time to put it into practice, right? And being able to write equations and balance them, whether or not they give you the name and you have to go to the structure or the compound, or they give you the compound and you have to figure out what the name is. All of that stuff we're going to do and be able to do it fluently. And then understanding the stoichiometry with respect to, again, the conservation of matter, right? Everything has to be balanced, same number of atoms on both sides of a chemical equation. Otherwise, you violate the law of the conservation of matter, all right? So with this writing and balancing equations, let's go ahead and jump in with that. And again, if the key to finding out whether you actually learn something is when you start being able to, and this is not an easy process, but when you're able to make the connection between, oh yeah, this is this. We talked about this, we just hadn't seen it in this way yet. When you start being able to make those connections and see the relationships between the stuff that was in the ether and now is real, that's how you know you learn some chemistry, when you get to that point. And it's a process, and it's reps, and it's looking at it and, you know, seeing it over and over and over again. But it's also seeing it in different contexts, right? Seeing it in different places in different ways, but understanding that it's the same concept, same thing. All right, so we're gonna start out with balancing equations and writing equations. Right, and again, when we think about a chemical equation, right, when we think about two atoms coming together, maybe A plus B, and they come together to make AB, something like that. Or we think about if we have something like AB plus CD and they react, and you get AD plus BC. That was not intentional, by the way. I just caught the fact that it's AD and BC. That was not intentional. But these are reactions, and the way that reactions happen is that atoms or elements combine with one another in different ways, and you get new compounds, right? And so normally when you write a chemical reaction, right, on the left side of the arrow, These are your reactants. So these are the atoms or elements that are bumping. And the way this happens on a microscopic level is that these atoms are crashing into each other, right? They're slamming into each other at very high rates of speed, very high velocities. And when they crash into each other and they collide, right? Sometimes they interact with each other and they make bonds, whether it be or whether it be an ionic bond or a covalent bond. And that's how you get products. That's how you get your new compounds on the other side of the arrow. So on the left side, it's always reactants. On the right side, these are your products, right? And then you have an arrow here indicating that a reaction is taking place. And sometimes, let's just say for the sake of argument that we put a delta here. That means that we've heated this reaction. So sometimes with the arrow, you'll also see the conditions, right? Heat, light, temperature, pressure, so on and so forth. Those are different conditions under which you do a reaction. And you always illustrate those conditions. You put them where the arrow is. Sometimes it can be above or below the arrow. It doesn't matter. And then sometimes you can see a reaction written like this, where you have AB. And then over your arrow, you'll have the reactants, CD, and then you'll have some other process at the end, like a quench or a workup. And then you end up with AD plus BC. So sometimes over the arrow, you'll see the reactants as well. So reactants are sometimes over the arrow, and that normally you'll see that more. That's more prevalent in organic when you're doing multi-step processes, right? But you'll see the reactants over the arrow, and then some conditions as well, right? So when you write a chemical equation, what you are illustrating are two things, right? You're illustrating the identities of your reactants and products. So every chemical equation is going to display these two things. First thing is the identity of the reactants and the products. Right. And then the second thing that a chemical reaction displays is the relative amounts of each substance. Right. This is that's where your stoichiometry comes in. When you talk about the relative amounts of each substance in a given reaction, that's where your stoichiometry and balancing comes in. Because the balancing is going to give you the stoichiometry. Right. So we talk about relative amounts of each substance. That's when we get into the concepts of balancing reactions and reaction stoichiometry, which is vitally important. Without the stoichiometry, there's just some certain things you just cannot tell about a reaction if you don't have the correct stoichiometry, right? So I'm going to put put a reaction up, and we're going to just walk through it. And we're gonna balance it as well, because I'm gonna show it unbalanced first. All right. So here we have methane. So CH4 plus O2. And that's going to yield CO2 plus H2O. I'm going to leave it like that. All right. So there's some things that we can talk about here. I put CH2, should be CH4, my bad. Make sure you correct that in your notes. That's a CH4, not a CH2. All right. So again, there's some things we can look at. This is an example of a chemical equation. We have our reactants on this side. You always write chemical equations from left to right. We have our products on this side. All right. If there's a plus sign here, what that indicates is these two reactants are combining. So this is indicating that a reaction is going to take place. Right. There's no plus sign, then there's no chemical reaction. There may be a chemical transformation, but it's not a reaction taking place. The plus sign means that these two things are coming together to do something, right? And they're going to get transformed into something else or converted into something else. And then we have a plus sign on this side. What that means is that you have multiple products. Right? You'll see me abbreviate this a lot. Products is PDTS, and reactants, a lot of times you'll just see it as R. All right. Always reactants on the left, products on the right, unless it's equilibrium. But we haven't talked about that yet. All right. Now, let's see if we can tally up the number of atoms on each side. So we're going to say carbon here. Everything on this side is carbon, hydrogen, and oxygen. And for the record, since we're going to be talking about classes of reactions. This type of reaction, whenever you see oxygen, like you see oxygen like this, molecular oxygen, 9 times out of 10. And then the products are carbon dioxide and water. Right? This is normally what we call a combustion reaction. It's a combustion. You see some type of alkane, like that CH4, that's just a what we call a saturated carbon molecule, which is normally called an alkane. I can go ahead and sneak that in to you. You'll learn it in organic, but why not learn it now too? That's any carbon containing molecules that don't have double bonds. So you got an alkane in the presence of oxygen, and normally you will heat this up. So there's some heat to get this reaction to go. It's called a combustion reaction, and the products are always the same: CO2 plus water. All right, so we got carbon, hydrogen, and oxygen on the left, and we also have on the right the same atoms. Now, how many carbons are on the left? How many carbons are in the reactants?
1.
1 carbon. How many hydrogens?
4.
4. Good. How many oxygens?
2.
2. Now look on the other side. How many carbons do we have over here? On the
One.
product side, 1 carbon. How many hydrogens?
2.
Two hydrogens. And then how many oxygens?
3.
3. We got a problem, right? What that's saying is that we've created a new oxygen atom out of nothing. We've also lost 2 hydrogen atoms, but we know that's not possible, right? These numbers have to match based on the law of conservation of matter, right? So the amounts or the number of atoms on each side, I put must in all caps, must be equal. Can't destroy matter, you can't create matter. So you have to keep the same number of atoms on both sides. That goes back to Dalton's law of indivisibility. It also goes back to the law of conservation of matter, which is one of the first things that we study. So what we have to do is balance the equation. That's the way you solve that, by putting in coefficients in front of the reactants or the products. You put numbers in to ensure that everything balances out. So for this equation, I'm just going to write it out. All right, so now let's go through and take inventory, because that's all balancing is taking inventory of your atoms. So balancing allows us to ensure that say again. So balancing allows us to ensure that the same number of atoms are on both sides. This number right here, we call it a coefficient. So that 2 here and the 2 here, we call that a coefficient. Right? And these numbers ensure that the number of atoms on both sides is identical. Right? So both sides, the number of atoms on both sides must be equal, because if not, we violated a physical law that is inviolable. We can't violate it. All right, so let's look at it. So we got carbon, same thing, carbon, hydrogen, oxygen, and then over here, carbon, hydrogen, and oxygen. How many carbons are on the left side? Still 1, is that right? Is that right? That's still 1 carbon.
Yes.
Right?
Yes.
Right side, still 1 carbon. How many hydrogens now on the left side? Did that change?
No.
Yeah.
Still 4, right? But the number of oxygen
Yeah.
is different now, right? It was 2, but now that because of that coefficient, we're going to take that and multiply it by that subscript. So now instead of 2 oxygens, we have 4 oxygens. Are y'all following that? That coefficient is going to change that.
Yep.
All right. So now let's look at what we got on the other side. Hydrogen wise, now we're going to do the same thing here. And I'm going to slow walk this down so make sure we don't miss anything. This 2 is going to be multiplied by that 2. So that means we're going to have now 4 hydrogens. Is that right? And then also, that's one oxygen there, but because of the coefficient, right, there's going to be two. And I'll show you what that means, right, in a second. So now we got two oxygens there, but we also have two here. So we're just going to say 2 plus 2. So we also have 4 oxygens. Are y'all following that? So the coefficient makes that the 2 oxygens from the water, and then we also got 2 from the CO2. So now we got a total of 4 oxygens on that side. So now this is balanced. That's balanced. The universe is happy, and we don't need the Thanos snap, right? We're okay now. All right. If you were to write this out, I'm gonna show you what this looks like. I'm gonna write it out in Lewis form, right? So this is CH4. Sometimes this helps to understand how to add the atoms up. And this is plus O2. So this is O, and it's a double bond, another oxygen. And that gives us CO2. So C is linear, not triangle, trigonometry. So that's CO2 plus 2 H2Os. So do you see now how the atoms, this is 1, 2, 3, 4 oxygens, is that right? And 1 carbon, and then 4 hydrogens. And on this side, even though the hydrogens are in a different molecule, it doesn't matter. We just care about the numbers, how many of each atom is on each side. We don't care about anything else. So here, we got 4 hydrogens, we got 1 carbon, and we got 2 oxygens. Right? So now when we talk about something being balanced, that's what that means. Same number of atoms on both sides. And even if we had to draw it out, right, that helps, because then we can see where everything is. But we know that everything is identical, right? And so when we talk about balancing the coefficients in the balanced equation, they help us. They tell us a lot. So those coefficients are actually, that's how we derive our ratios. So they give us our stoichiometric ratios. Right? That's very important. That's why when we do chemical reactions, they have to be balanced, because the ratios give us all types of data, right? They give us what the theoretical yield is. They give us what the limiting reagent is. They give us what the excess reagent, all of that, all those things can be determined from those ratios. So ratios are important. So they tell us about the, excuse me, the theoretical yield, the excess reagent, the limiting reagent. We're going to talk about all these things. Right? They tell us a lot. That's why we need to understand balancing and why it's important. All right. So let's look at what the ratio, what is the ratio of, in this equation, CH4 to water. based on these numbers right here, the coefficients, what's the ratio of CH4 to water? And if there's no number present, we know now at this point, we should know that it's understood to be 1. So there's an understood
A
1.
one.
Go ahead.
So it'd be a 1-to-2 ratio.
1-to-2 ratio, right? That's very important. What's the ratio of oxygen to CO2? So there's a, look at the coefficient in front of oxygen. There's a 2 there.
2-to-1.
2 to 1, right? What's the ratio of CH4 to CO2?
1-to-1.
1 to 1, right? That's why those coefficients are important, because think about it this way. When we know what the coefficients are, and if they're the right coefficients, remember how we manipulated grams over molar mass to get moles, and moles over liters to get molarity, and we can find one thing in relation to the other. That's what those ratios allow you to do. They allow you to figure out how much oxygen it would take to create X amount of water, or how much water is created from X amount of CH4. So those ratios tell you the relationships between all those substances, and you can interconvert between them. So if you want to know how much oxygen you're going to get from CH4, or how much CO2 you're going to get, the relationship is 1 to 1. Let me show you. Let me just copy this if I can. How can I erase all this crap? All right. So what if I say that the relationships right, or given by the ratios, if I want to know the relationship between CH4 and CO2, what I can say is that since they're in a 1-to-1 ratio, I have 1 mole of CH4 equals 1 mole of CO2. Right now, let's say, for instance, I'm given 35 moles of CH4, and I'm asked how much CO2 I'll get from that. So if I'm given a number, this is how we take these ratios and apply them, right? Right, because those ratios don't change. Those are relative numbers, so they won't change. But I might start out in a lab, I might give you 35 moles of CH4. And this is the equation. And I want to know how much CO2 is formed. I can interconvert between those using the relationship. So 1 mole of CO2 over 1 mole of CH4, because I'm trying to get rid of that, times 35 moles of CH4. Is that right? So if I'm given 35 moles of CH4, I can answer this question if I know the balanced equation, because moles of CH4 cancel, and obviously the answer is 35 because they're 1-to-1. But what if the question was, if I gave you 35 moles of CH4, how much water would we get? All right, we can answer that question. Right? We know that the relationship between CH4 and H2O is what? What's the ratio?
Wait, say that again.
What's the ratio between CH4 and water?
1 to 2.
1 to 2. Right? So we can actually figure this out. How much water we get if we started with 35 moles of CH4. We could come in and say, well, I could just take the relationship between those 2 moles of water and divide by 1 mole. This is the ratio, right, of CH4 times 35 moles of CH4. I'll cancel that, right? That's how we apply these numbers. That's how, when we balance an equation, that's the purpose of it, because you can use those ratios that you get to interconvert and show a relationship between any of the reactants and any of the products. And that's the purpose of all of that, right? It seems mundane initially, but most of the times, once you balance it, you can find a lot of information out. Like there's a lot of data that you get from a balanced equation. All right, any questions so far? Right, that's kind of a tangent, because that's again, when we start talking about stoichiometry, that's what we're talking about, the relationships between the substances. So I'm kind of combining that, even though we're going to come back to that, but there's no sense in making you wait if we can look at it right now. Any questions about anything? We've already dealt with moles, haven't we? We've dealt with moles. We've dealt with how to convert moles into molecules, how to convert moles into grams. Even if it said we had 35 grams of CH4, we could get to the moles, couldn't we? Because if we know CH4 molar mass, which is 16, we can get to the moles from the gram. So anything that's given to us, we got a way to derive what we need, just based on the few little relationships that we've already studied. Molar mass, Avogadro's number, percent composition, all that type of stuff. We can get to anything. So there's nothing that can stop us from figuring out any one of these, any questions dealing with moles, mass, grams, molarity, nothing. The only thing that can stop us is us. All right. Let's do another example. One that's not so well, it's a little bit mundane, but it's not so trivial. So let's do another example. So let's take water. And let's split it into hydrogen gas. And this is actually a real process. We actually took didn't I give y'all a quiz on that? That was a paper that I posted as a quiz, dealing with converting water, taking water and turning it into hydrogen gas, or taking hydrogen gas and oxygen and making water, one or two. It was way back. I think it was the first quiz that we took, maybe in the second quiz. But anyway, this is like something that is a real research field, splitting water up into and converting it into hydrogen gas, oxygen gas. So is this balanced right now?
No.
It's not. If we look on the left side, we got hydrogen and oxygen. We got 2 hydrogens and 1 oxygen. If you look on the right side, we got 2 hydrogens and 2 oxygens. That's a problem. We cannot create atoms out of thin air, and we can't create matter out of thin air. So the way you remedy that is to balance the equation. How would you balance this? What would you do? There's so many different strategies for balancing, but I just like to look at what we have and then try to figure out how to make it equal on both sides, right? So by using kind of like first grade math or second grade math, at least using like a least common denominator method, where you find a number that both of the atoms can be equal to, right? So in this case, what would you do? How would you get the same number of, and you start atom by atom, but let's say, how would you get the same number of hydrogens on, oxygens on both sides?
Use 2 as the coefficient in front of water.
Okay, so if we make the coefficient, very good. If we make the coefficient 2 here, now that's going to affect both atoms, right? It's going to affect the hydrogen and the oxygen, right? But here we're going to do maybe 1 times 2. So now we got 2 oxygens, and this is going to be 2 times 2. So now we got 4 hydrogens. On the other side, what do we need to do? Because the oxygens are balanced now.
Put a 2 in front of hydrogen.
So if we put a 2 here, that's going to make that into 4. And now the equation is balanced. All right. So when we look at an equation like that, it seems mundane, it seems simple, but it's the practice of figuring out how to make both sides equal. All right. So let's do another one. Let's take we got 3 minutes left. Didn't even think we'd get this far, but I'm glad we did. We're gonna work through some more of these on tomorrow. Balancing is like it's your life right now because it's the most important concept from this section. It's balancing equations, because the nomenclature and the naming, that just takes practice and reps, but the balancing part is important from this point forward, because you cannot do anything else. You can't do kinetics, equilibrium, any of that stuff without knowing how to balance an equation. All right, so let's take another example. All right, how would you balance that? Well, first we need to figure out how many atoms are on each side, right? So this is N, this is O, and there are 2 nitrogens and 2 oxygens. And over here, you got 2 nitrogens and 5 oxygen. So let's balance oxygen first and then go back and do the nitrogen. How would you balance oxygen? You have a 2 on one side and 5 on the other side. Like what number is common between those?
10.
10, right? So if I wanted to get 10 oxygens on the right, right, what would I do? What number would I put in front of N2O5 to get 10 oxygens there?
5.
2, right? There's a 5. It's O5. So this is 2 times that.
Oh, I thought you were doing the first part.
Oh, no, my bad. Yeah, I was talking about the product. I know that you knew that though, so I ain't tripping. All right. Let me move this over. So this is N2 now is going to become what? Because of that coefficient of 2. That's going to be times 2. So that's going to give me 4. And then N2 times 5 is going to give me 10. So now I got 4 nitrogens and 10 oxygens. What about the left side? What do I need to do to that? That's easier than the other side, isn't it? Because I can work with the individual molecules. Is that right? So if I want to make 4 nitrogens over here on the reactant side, what would I do?
Put a 2.
A 2 here. And then what about the oxygen? So that's going to be 2 times 2. So that's going to be 4 nitrogens. What about the oxygen? I need 10 of
5.
them. I'll put a 5 in front of it. Good. Excellent. You're going to be my resident balancing tutor. Put you to work. This is you're on point. So yeah, so now this is balanced, right? You got 4 nitrogens on both sides. You got 10 oxygens on both sides. So now it's balanced. And again, the strategy I like to use is to look at the subscripts and figure out like, or look at the number of each atom and figure out if there's some common denominator, there's some common number that I can shoot for both of them. That's not always feasible because sometimes you have to use fractions when you're balancing. And yes, you can use fractions. It doesn't change anything. We're going to do some examples with fractions on tomorrow. But yeah, so this is good. So always we're going to keep practicing this, keep getting more reps, keep talking about the different concepts, stoichiometry and things like that. Because all this is it's all tied in together. The coefficients, those are my end up being my stoichiometric ratios, right? What's the relationship between the ratio between molecular oxygen, so O2 and N2O5 in this equation?
Five to two.
5 to 2. So let's say I gave you 100 moles of N2O5 as the product. How much oxygen did that come from? We could figure that out, couldn't we? Just take 100 moles and multiply it by, put the 5 in the top and the 2 in the bottom and cancel out the N2O5s. We can figure out how much oxygen that is. So all these relationships matter. So balancing that's the importance of balancing, is figuring out the relationships between the atoms and the molecules that are reacting. All right, so we got to stop here. We are 3 minutes over time, so I'm gonna